All right, so welcome everyone to the fourth session. This is the programming interview easy session. So the way this actually would work is that we've shared the questions already up front, so you can see that these are the 5 questions that we'll walk through. Given that this is about an hour's worth of session, there is a lot of content and material that we need to cover. So what I will do is I'll just quickly run through the first few questions, and I want to spend a little bit of time on the last two, essentially, the QuickSort and the QuickSelect. All right. So before we jump straight in, some of you, I think this is the first time you're joining. So welcome to SDE Skills. It's a 501c3 nonprofit organization. We have been set up specifically with a singular goal of essentially improving skills for engineers and primarily focused on the interviewing skills. This session is actually online, and we run a few other online programs as well. If you are based out of Seattle, then please feel free to, in and around Seattle area, please feel free to join us on the meetups that actually happen in person. So before we, so what I'll do is let me just go through the session, and then I'll probably leave some time, about 10 minutes or so, like after the recording is terminated, for taking any questions if folks have. All right. So jumping right ahead, the very first question that I wanted to cover today was finding the largest number in an integer array. This should be a very straightforward question. Anyone has any suggestions as to how to do that? Any thoughts? Should be straightforward.
I think we could go through, like iterate through the array, and then have an if check. If any of the value in the array that is greater than the max, then we want the max to be that value. So just reassign that max until you get the largest one.
Fantastic. What would be the edge cases for this particular code?
So first of all, is that even an array? We can check. And then if the array is empty,
what else?
Is there any duplicate?
Why would there be a problem if there's a duplicate?
Then you want to select only one of it, right?
But max is max, right? You're returning the largest value, so you
should okay, so it's the either one. That's fine. Yeah.
So if there's only one element, then that element is the maximum element?
Correct. And what would you initialize max with?
0.
Is that okay?
Mm-hmm.
Okay.
What is the data type?
Oh, no, actually the first element, I think, because we started with the index 0. So I think like max with the first element.
Wouldn't it be int, the minimum value of an integer, if int is the base, if it's the value, yeah, it's an int. So it'd be mint, the minimum value of a mint, of an int.
So you have 3 choices, right? So someone said initialize with the max with 0, which probably is not a good idea, because if you have negative numbers, you will miss it. And someone said, let's initialize with minint. And then the third option is essentially saying, let's initialize with a of 0, which is the first element. Which one is preferred between minint and a of 0?
We'll say a of 0, because how do you know what is int? Like,
minint in most languages, you already have like a constant that is defined, which represents the lowest possible value that a particular value number can have. So Java has minint and maxint. Certain languages have different ways it's called. So you will know how to do that. But in general, one of the things to look at is that, so in this case, the comparison is very straightforward, right? So you're looking at largest number. So I clearly know what the smallest number looks like, so I'm able to assign it. But if I have a slightly different context of where you're trying to do a different comparison, like, find the best something, in that particular case, it's very hard to figure out what the lower value or the lowest value looks like. So it's a very common practice when you're doing this sort of like, find the largest or find the best kind of a scenario. You set it to the very first option that you have. And that just works very well in so many different cases. So I think either one will work, but I personally prefer setting it to A of 0 after you check that the array is not empty. If the array is empty, then you return like there is no large value, so it's either an exception or something. But if the array is not empty, then you can take the first element and then put it on A of 0. Okay, and that should work. So this is good. So let's actually jump into the second question, which is like, how do you find the second largest number? Now that you know how to find the largest number, how do you find the second largest number?
One quick way is we can just find the max and then we remove the max from the array and then find the max again from the remaining array.
How would you remove the max?
Well, I would simply have two values, the first and the second, and the first value is the maximum, and then if I find and then the second value is the value that's less than the next value I find that's lower than the maximum. When I check the third value, then I just see, does it replace the first, or if the third value is less than the second, I'm done. If it's not, then I just need to see whether it replaces the second or the first.
Would it replace the second, or so if it replaces the second, then the second will become the first, right? Or is that
right? So if we've got 5, 7, 2, 7 is the highest, 5 is the next. When I hit 2, it's less than 5. I don't need to do any more testing.
Mm-hmm.
If it's higher, if the third value were higher than 5, then I have to figure out, does it replace 5 or 7?
Okay. If it's larger, like if it's 8?
Then it replaces the 7, and the 7 bumps the 5.
Right. So it replaces 7, and 7 bumps the 5, right?
Right.
So
but we only have to. But the idea is that we don't even bother testing if it's less than our number 2 choice.
In the third, in this case, in the
right.
In the line
for the third value.
Yeah. Totally makes
yeah.
sense. Like you're checking if it's more than 5, like more than a smaller value, then replace it. If it's more than the greater value, then you replace and bump. Yeah, makes total sense. What is the time complexity of this operation?
O of n.
O of n. Okay. How is it O of n? You're going through the loop only once. Is that why?
Right.
Okay. What is the space complexity of this?
Should be simple because we're not storing much data. It's just the array.
So essentially, it's like constant because you're using 2 extra spaces, but it's just constant. Fantastic. Okay. So we won't write this. Go ahead.
I have a question. So with all these questions, finding the largest and the second largest, can we just not sort the...
Can you say that one more time? Sorry, I have somebody who was giving echo on mute. Go ahead.
So with all these like first 3 questions, can we not just sort these arrays and then take the first element or take the second element?
Fantastic point. I was actually wondering when somebody will actually come up with that. Can I just sort the array and then pick the second element? Pick the second last element, basically. Of course I can do that. What is the time complexity of that operation?
Depends on how you sort.
What's the best sorting algorithm that you know?
So n log n?
It would be typically n log n. I mean, there are different sorting algorithms. Your merge sort, QuickSort, and there's apparently insertion sort, tim sort. There are a bunch of different types of sorts. They give you n log n complexity. So more or less. What about space?
No additional space required because we can just sort the array in place.
That's cheating. in most interview questions and in interview cases, if you have an array and you have the data set, you are not permitted to destroy the data set. You're supposed to keep it intact.
Okay.
So you are expected, so you will essentially have a O of n space because you will be using something. So that's one way of looking at it. There's only one exception to this sort of a rule is that I have seen interview questions where as long as you leave the input in the same state that you found it, it's okay, or something like that. So there is one of the interview questions where it's all positive numbers, and what you do is that you use some sort of like math magic to convert that number, to flip that number to negative or something like that. And then at the end of the question, you just go back and set every number to its absolute value, and that's considered O of one space because you actually technically did not use any extra space. You did modify the input array, but you also unmodified it or modified it back to the original one. That's acceptable. But in most common terminologies, this is the O of n space. So that's why you wouldn't do sorting. But that actually got you to the question number 3, right? If I ask you to find the kth largest number in an array, then fantastic. Sorting just works, right?
Yeah.
What else can you do if you don't want to sort?
You have to sort all the elements, and then whatever the approach we used, find the second element. So then we need to find the position, whatever the position you are expecting.
Yeah, for Q3, you can absolutely, sorting works, and the time complexity is n log n, and you can find the kth element from the sorted order. It's absolutely fine. Can you do better than that? Can you do something without sorting?
Without sorting, so for each element we need to compare and we need to create one more sorted array. That is one way.
Is there a data structure? So I know this is a programming interviews easy session, but is there a data structure that actually will help you with identifying, with actually finding elements that are larger than a specific number or smaller than a specific number?
A min heap or a max heap?
A min heap or a max heap. What is a heap?
It's a tree that falls. It's a tree data structure that always keeps the min or max at the. It's a tree. I would say it's a binary tree.
Mm-hmm. So a heap is a data structure. Let's actually assume that let's go with a min heap. So min heap is essentially like a data structure which contains a bunch of elements, and the top of the heap is the only thing that's accessible to you, and that is guaranteed to be the smallest of all the elements that's inside that bag. So think of it as a very opaque data structure, and the smallest element is in the top, and every element inside the bag is actually greater than the top of the heap. So that's all you need to understand what a min heap looks like, and its implementation is actually through a tree and whatnot. There's a way of actually creating that structure and editing it and whatnot. We'll get there. Anyone not following what a heap is?
Right, but a heap by default is a sorted structure. So whether you use a min heap or something else, you're still sorting the data.
Not true. A heap, so without going into too much of detail, a heap is actually not necessarily sorted intrinsically. A heap will only give you the smallest number. It doesn't give you the second smallest, the third smallest, or the fourth smallest. You will have to pluck the element out of the heap to do something with it. So the thing with heap is that the heap actually defines an operation which is essentially saying let's talk about min heap. So the get top, which essentially will return the minimum value, this complexity is O of 1. It's a constant complexity of giving you the topmost element. Okay. The next thing is actually insert into heap. Okay. And then once you do that, you have to do what's called a heapify operation, which actually resets everything else. What's the time complexity of the insert into heap operation? Any guesses? It's actually O of log of,
n.
not n. I don't want to use the word n because n is already there. I want to say log of x, where x is the number of elements in the heap. Right?
Mm-hmm.
Okay, and what about remove element from the heap? Same thing, right? Okay,
But
so now
you're still going to have to put every element in the heap first before you can get them in off.
Not yet. Let's figure out, right? So let's do that. So what you do is you take the first k elements and put that in the heap. What do you think is the cost of putting all the k elements in the heap? It's k times log k, right? If you put all the n elements in the heap, it's n log n. But you only put k elements. The cost of putting this thing is essentially k log k. What is this? This is the cost in terms of the time complexity. What's the space complexity? It's just k. It's not n yet. You just taken the first k elements and put it there. Now what you do is that you take the k plus first element and you compare with the top of the heap. So what do you know? You know that the top of the heap is the smallest element. Every element in the bag is actually greater than the top of the heap. Now, if the top of the heap is actually smaller, is actually greater than the k plus first element, then you can just discard it. Just like how you discarded 2 in the example above, because 2 was smaller than 5 and 7, just comparing at the top of the heap, you can just discard it. Make sense? Then what you can do is, if not, right? If not, so if k plus, if small, then discard. If large, then what you do is you actually remove the top element from the top of the heap, insert the k plus 1 element, and heapify. Heapify is the one that actually rearranges everything. So what do you think is the operation? What do you think is the time complexity of this operation? It's log k to remove the element plus log k to insert the element, essentially, and you're done.
So essentially, that's the same as the comparison we did up above on lines 41 to 43. You're just using the heap to figure out versus doing some other logic.
Correct. If you had used some sort of an array logic, then it will be n times k, because you have to go through the process to figure out where to do it, right? Imagine you had used some sort of like a binary search tree or something to figure out. You could have done that. Instead, this one actually gives you n log k. It's not n log n. If k were to be something that's significantly small, like if it was like 10th largest, 15th largest or something, then a n log k would actually be better. Like if very commonly this is used, like, find the top 10 products that are trending or the top keywords that are trending, you would just use a heap to keep track of that. So since you're talking about top 10 or top 100 amongst a million products or whatever, this would actually, the log k will actually disappear as a constant. So you wouldn't actually have much of a time complexity with it. So technically, if you were to insert the entire thing in a heap and you did it, that's as good or as bad as sorting. And that would be n log n. But since you're using a heap of a limited size, this is n log k. Does that make sense?
Yeah, so quick question there. So when we are saying that if the element is larger, then remove the top elements and then insert the elements. So you mentioned that the time complexity is log k for removing the element, but would it not be just the order of 1 because we are just removing the top element. So we are not going through the 3 elements then?
No. If you remove the top element, what happens? Actually,
Then it's order.
It has to heapify again, right? Because you need to figure out what element needs to replace the top element. The heap.
Yeah, but then we have the second log K, right, for that when we are inserting and heapifying. So the first log K should basically be just order of 1, right? So we are just removing the top element, that's it.
In theory, you can do that. But the challenge that you have is that so essentially what you've been doing is you're just replacing the top element with the K plus first element, which will essentially create an imbalance in the heap. And then you're essentially making the heap sink down. So theoretically, you can have a way of doing it. But normally what happens is, invariably what you do is you do a delete, and then you heapify. Essentially, it fixes the heap. And then you insert, and then fixes the heap again. So you will essentially go from a heap of size K to a heap of size K minus 1. And then it'll go again back to heap of K. And worst case scenario, the data has to flow down all the way, resulting in a log K operation. So if you use an inbuilt data structure, you don't have a good way of doing without doing this. If you're building the heap yourself, then you may have an ability to replace. You can do a replace the top of the thing with a different value as a single operation. You could potentially simplify it, but what is the time complexity difference between log K and twice of log K?
Nothing.
Constant, right? Yeah, it's constant, right?
Yeah.
Constant times log K is the same. So technically it is log K. All right. That's why you'd look at this as n log K.
Yeah. Right. Okay.
All right. Awesome. So this is interesting. So now let's actually any questions on the heap? Because I think I just wanted to introduce this as a data structure. Heap is a very interesting data structure. There's a whole bunch of stuff about heap. I know this is the easy session, so I didn't want to talk a lot about it, but just from a mental model standpoint, if you want to use a heap, all you have to do is think of heap as a data structure that actually will give you access to the smallest element in case of a min heap, and everything inside the bag is actually larger than that. And there's a tree-like data structure that can be used to construct this. And there's a tree-based one, there's an array-based one. There are a bunch of different ways you can do that, but that's a different problem for another day. So any questions so far?
Nope.
All right. Fantastic. So let's actually now go, and we talked about sorting algorithms, right? So let's jump to Q4, which is QuickSort. Can someone actually explain what is QuickSort? Hey, Shrikant, I think it's just you, because are folks able to hear me?
Yeah.
Yeah, folks are able to hear me, so go ahead. So can anyone explain what a QuickSort is? Any takers? Even if you're wrong, that's okay. I can help you correct.
Yeah, actually, choose an element as a pivot. So maybe any element from the array. And then you compare all the numbers from the beginning with the pivot. So as long as the number which is from the beginning, if it is less, you keep incrementing the counter from the beginning. The moment like you find a number, you are going from the left to right. So let's say like if you choose the number, if you get a number which is, if you get a number greater, then now you start keep that index, and then now you start from the back another counter.
Which one is pivot in this case? I just have an example in front of me, which is 16.
Take the first number as a pivot.
Okay.
So now then you start comparing from the second, right?
Okay, I start comparing from 2, and what's the other one?
The other one is like comes from the back. So let's say like I is the counter which is now at 2, and then you have a counter j which is at 16.
Okay, so I have the point at 16. Go on.
Yeah, so now start So 2 and pivot. So you compare. As long as 2 and 15 is less, so 2 is less than 15, so you increment the counter. 7 is less than 15, and 20 is greater, so you stop there. Now you start comparing the element from the back with the pivot. So now what you do is like when you are coming from the back, like as long as it is greater, you keep it decrementing the counter.
Okay.
So the moment you find a number which is smaller.
So I found 10. What do I do?
Yeah. So now you found 10. So now what you do is you swap 10 and 20.
Okay. So I made this 20. I made this 10. Now what?
Okay. So now you keep continuing. So now go to your increment I.
Okay. I went to 15. Now what do I do? 15 is equal. So what do I do?
Okay. So 15 is equal. So I think you can still continue because it's already in the position.
Okay.
So now 19, right? So 19 is greater. So you stop. So now continue from the back. So 15
is equal. What do I do?
Okay. So 15 is equal, right? So now you swap 15 and 19.
Okay. So, but last time when it was equal, you said it was okay. So why so?
Yeah, I mean, okay. I mean, so even if we, okay, so I think.
So yeah, we gotta keep an equal to sign on either side, right? At least.
Yeah, I mean the
either
idea
in the left side or in the right side, right?
Not on both.
Yeah. No. I mean, if it's both, then so we are not essentially swapping, right? It's the same thing then.
So
I think.
So Ram, you're right. Let me actually take a step back and kind of walk through what the algorithm does. But fantastic. I think this is right. So this is the first step of the algorithm, and we can continue. So the goal here is this, right? We want to find a way to somehow, if you have a mechanism, right, that can split the array into all the elements that are smaller or equal to the pivot on one side, and then you have the pivot in the middle, and then you have a larger on the other side. If you can split your array into 3 parts, one part which is the left half or left side which contains smaller or equal, and then the pivot, and then the right side which is the larger element. So these, if I can magically figure this out, right, that's great. Then what I can do is that then I can actually repeat the same sort operation in the smaller one separately and the larger one separately. So QuickSort is a divide and conquer approach. In theory, you should be able to get to 50%. If you are able to divide the array into exactly 49, 1, and 49 or whatever, like that kind of a breakdown, then it's just simpler for you to, like, the array will just break down, and you will be getting a sorted value. So if I can, now my job is to sort this half array. And can you think of an algorithm that can actually help you sort? Can you think of an algorithm that can actually help you sort this half array? This is QuickSort again, right? So you can recursively call QuickSort on the left half, and then you could call the QuickSort on the right half, and continue. Now, one problem which exists with this is that how do you pick this pivot? Unfortunately, you wouldn't know what is that exact element that actually will divide your array into exactly the equal left half and equal right half, and that will be a problem, right? So what we do for that is we don't really know. So we just pick a random number, and in this case, Ram picked the random number of 15, which is the first element. You might have as well picked the last element, which is 16, or you could have picked any random element, 10 or whatever. So what it will do is that it will divide the array into 3 parts, again the same thing, smaller or equal on the left hand side, pivot in between, and a larger one on the right hand side. But the only difference is that unfortunately, what if you're let's say you randomly, your luck was terrible and you picked 2 as the pivot, then what you need to see is you need to have essentially you'll only have 2 on one side, then you'll have the pivot, and you'll have the entire array on the right hand side, and that's what will happen. Now, unfortunately, you wouldn't know how to make these swaps happen. So what we do instead in this particular scenario is, that's why you first find a pivot, and then you move the pivot away. So let's assume that the 2 was I'll pick a different number. Like let's say 7 was the pivot. So you take the 7 and you move it away to the first element. Okay. And then what you do is, and then after you do that swap, then what you can do is you can actually use this 2-pointer technique that Ram was just walking through, and then you sift this entire array in such a way that all the elements in the beginning would be less than 7, and all the elements in the right would be greater than 7. Essentially, after you're done with it, this is what you'll be left with. Now what you can do is you can take this pivot and just prop it at the right spot wherever it just needs to go, and that's it. So essentially you will replace this 2 and then it will replace the 7. That's it. So what you're left with is you're left with all the numbers less than 7, the 7 itself, and all the numbers that are greater than 7. Please note that the left half and the right half, the left array and the right array are not sorted yet. Okay, and then you can recursively use this to do the quicksort. So any challenges or any concerns with the quicksort?
So when do we stop?
When do you stop? When do you stop? When do you think we should stop?
I mean, when we can have like one, so when we can have like one element left for each?
No, when the quicksort of one element is just return the element itself. There's nothing, right?
Cool.
And quicksort of 0 elements is also nothing. Quicksort of 1 element and quicksort of 0 element is the same array itself. So if I give you 2 elements, what do? If I give you like say 5 and 5 and 2 is what I've given you. Okay. Now what you'll do is you'll randomly pick one pivot. Let's say you pick the pivot of 5. Okay. So what's your next step? You pick the pivot of 5. Your left array is 2. Your right array is nothing. Right? And now you will essentially try to sort the 2. And when you sort the 2, what do you get? 2 itself. And then you have 5. And that's it. So you stop when you have 0 or 1 elements. And even with 2 elements, you will essentially continue the same operation. Since you're actually taking the pivot out of the equation every time, you're always, with every step, you're at least guaranteed to reduce the size by 1. Okay? What is the worst case complexity of a quicksort?
Order of n?
N square.
No, it's n square, not n, right? Because imagine what happens, like, you know what, you had terrible luck and you picked 2 as the pivot, okay? Or rather, no, you picked 20 as the pivot. Guess what happens? You have the full array here, you have 20, and then you have nothing on this side. Now again, your job is to sort this full array, right? Let's assume that you have terrible luck and you pick 19 as the pivot. So what you have is, again, you have like the mostly the large array, 19, and then you have 20. Then you have terrible luck, and then you did this. So essentially what are you doing? You are essentially, each step you're only eliminating one value, and for the sifting operation, right, for figuring out whether the element needs to go from to the left or you want to swap or not, you are reading the entire array once, right? So between that and this, it's actually n square operation. So for every row, 71 is a O of n operation, 72 is a O of n operation, 73 is a O of n operation, and so on, and that's why it is n square. Now, if you got perfectly lucky every time, and you always like manage to divide your data set into half every time, like you started with 1,000,000 entries and you magically got the best pivot that divided into 500,000. On left side and the right side, you magically got the exact number that you needed that actually also got you like, you know, n by 4, n by 4, and so on and so on. So when do you think it will actually diminish? How many lines do you think you'll have in that case? Like each time you're just going by half, right? So when do you think you'll stop?
Is it log n?
It is log n. Since you're halving every time, if you have, for example, if you have like 1024 elements and you keep halving it every time, essentially you're not halving it, you're actually doing half minus 1, like n minus 1 by 2. But let's assume, let's ignore the minus 1 at this point. 1024 becomes 512, becomes 256, becomes so on. In 10 steps it will go down. Now instead of 1024, if you had 2048, you will actually require 11 steps, and this is essentially log to the base 2. Right. So every time, if you're dividing it by in half, you will essentially make it it's a log n operation. So each row is essentially a n operation, and each number of rows that you have is a log n operation. So QuickSort in the best case will actually give you n log n, and in the worst case it will give you n square. Okay. So far so good. All right. So now let's actually jump to the question, which is essentially, how many of you have you heard of something called QuickSelect as an algorithm? Maybe, maybe not.
No.
Not at all. Okay. So what we do is let's talk through this. So remember the question that we had before. Find the k elements, right? Of this. So in this array, if I ask you to find, let me just make it a little different, okay? So in this array, let me ask you to find me the largest 3 numbers. What are those? Essentially, it's 15, 16, and 19, right? Right? Okay. So now, the way you can actually think about this is that just like how we thought of heap, right? There's a different way to look at this. Now let's assume that we do the step 1 of QuickSort. Okay? And somehow, magically, so the QuickSort is supposed to divide this array into like an array of size A, and then there's a 1 pivot, and then B, right? That's what it does. It splits your array into 2 pieces, right? It splits your array into the small array, which is A, and the larger array, which is B. Okay, I'm going to call it like the small array and the larger array. Now, what if you actually found you have like, let's say case 1. You found the magic pivot, in this case, which happens to be, I don't know, 12. Okay. What that does is that the size of the larger array is exactly equal to k. What does that mean? Or rather k minus 1. What does that mean? The pivot is the answer, right? To find the kth largest number, if you know that there are k minus 1 elements that are larger than you, then pivot has to be the kth element, correct? So if I wanted to find the 4th largest element, that was the question in this case, if I were to do that, and the magic pivot was 12 itself, then that's fantastic. But hey, you know what? Our luck may not be that right. So let's do case 2. You pick a pivot that is that's actually smaller than 12. You just picked 8, for example. Okay. Then what happens is that you have a small array. You have 8, and then you have the larger array. But how many elements are there in the larger array? In this case, more than 8 is like you've got 10, 11, and 12 added to it, right? That's it. Right? So 1, 2, 3, 4, 5, 6 elements are there. So essentially, you have 6 elements in the larger array, and you still have to find the 4th largest value. Now, do you think that the 4th largest element in the larger array is the same as the 4th largest element in the full array? Anyone disagrees? Like by taking the largest value, by taking any random pivot. You picked a pivot of 8. So what you found is that the fourth largest element in the full array that you have of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 elements is the same as the fourth largest element in the 6 array, right? Array of 6 elements. Because you got all the big numbers on one side, right? And then, so now what you've done, you've actually taken a problem which essentially was to find 4 among 11, and you've reduced it to 4 among 6. Okay. Now let's do one more thing. Let's do the case 3. And let's say in case 3 you picked a pivot that is 16. Okay. So what happens is you have the small array here. You have 16. And then you have the larger array, which is essentially just one element here at this point, right? So now what you know is that you were supposed to find fourth largest in 11, okay? And you know that the larger array here, which is like one element in this case, is definitely larger, and 16 is also larger than what you wanted. And so now finding the second largest in the small array will get you the same thing. That work? So let's see how this actually, and that's it. That's about it, right? So let's see how this actually works. So this is called the QuickSelect algorithm. So when you do QuickSelect of, essentially you want to find the array, okay, and you want to find the kth element, right? This is what you want to do. So first thing what you do is I am going to split the array with random pivot, okay, into small, large, and pivot. Okay, that's what I did. Now, if large is the size or length of, I'm just using some arbitrary notation, but you should be able to translate this to code. If this is exactly equal to k minus 1, then return pivot. Okay, if size of large is greater than k, greater than or equal to k, then return QuickSelect of the large array and k. Otherwise, it's the third option, so I don't have to do that, but I can say otherwise new k is actually k minus size of large minus 1, return QuickSelect of small new k. And that's it. And that's about it. Any questions? So let's try this. So one of the things I can do is let me just sort this array. So you have 2, 7, 2, 5, 7, 2, 5, 7. There's 2 2s, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I've got all the numbers here, right? Okay. So first is let's pick a random pivot. So when I'm using this notation, it just means that the elements are completely shuffled. Okay. It doesn't mean it's sorted. So what is the first step? The first step is essentially pick a random pivot, and I want to find the fourth largest element in this array. Okay, my random pivot happens to be 7. So which case is this? 1, 2, or 3? Which case is this? It's the second case, right?
Yeah.
So what do we need to do? Which means finding the fourth largest element of this array gives me this step. So which means that it's the same as fourth largest in the large array. That's it, right? That's what we did. Correct? That's this case. Now, let's pick another random pivot. And I'm going to pick 16. Okay? And I'm going to pick 15. Let's do 15. Okay? So what it does is, small is this guy. Large is this guy. And pivot is 15. So now which case is this? Case 3. Right? So new case is what? New case 4 minus size of large, which is 2 minus 1. So which is 1. So essentially now the problem has reduced to find the largest element in the small array, essentially, right? So essentially your goal is now find first largest in this is what you need to do. Okay? Let's also find the pivot, a random pivot. So we don't optimize at this point, we just find the pivot. Now I find the pivot of 10. So what it does is small is 8, large is 11 and 12. This is case 2. Now again, now this time I find the value is 12. So in which case what happens is, this is case 2. So find first largest in 11, 12. Then I do random pivot of 12. Small is 11 and large is empty, and this is essentially case 1, which is the answer. So now I found the value is 12, right? Which is the correct answer. 12 is the fourth largest element in this particular case. So any questions on this operation? And I went a little fast, but I just wanted to walk through the example. It's not super hard because essentially what you have done is you have it's the first part of QuickSort where you partition the array, and then once you split the array into the small array, the pivot, and the large array, you just have to now change your selection problem into the new problem based on how it happened. If it magically split it exactly, then you're good. If it doesn't, then you have to either do a quick select on the small side or the large side, right? What's the time complexity of this operation? Any thoughts? So how many, what's the length? How deep do we need to go? Worst case is K, because let's assume that every time you got so unlucky that you got the largest value every time, right? Then you will go down K steps, because every time you will essentially go, you check out the pivot, and you have the small array which is just like, n minus 1 every time, right? So that's the worst case. But in a typical case, you will essentially be done in like just a few iterations. And the expectation would be that, and also that each time you are looking at O of n pass to go through to do the split. In order for you to do a split, you have to do an O of n pass, right? So this QuickSelect algorithm is expected to run in O of n times, essentially times constant. Worst case is O of nk. But typical time is essentially O of n. So QuickSelect actually is in place O of one space because it's in place, assuming you can destroy the original array, and it is a O of n time complexity. Any thoughts? All right. So what I want to, so I think this is like a very simple algorithm. It's not complicated. It's got like a bunch of things going on. The only aspect of why this is actually interesting or why it's a little difficult to wrap your head around is about how the recursion works. I would strongly encourage each one of you to go and try this out in in whatever language of your choice. Write the QuickSelect algorithm. If you know how to write the QuickSelect algorithm and the QuickSort algorithm from ground up, I think you will completely make sure that you understand recursion very well, and you understand essentially these two algorithms which actually form a part of multiple different types of interview questions. So I think these are not on the easy scale. They're definitely not. I know it's a programming interviews easy session, but these are slightly on the moderate to hard side of the story. But at the face of it, I mean, these algorithms are actually super simple. If you can solve these questions, then it'll give you like a much stronger leg up in terms of understanding other algorithms which are based on recursion. All right.
Mm-hmm.
So any questions on these questions that we covered today?
So Vivek, how did you get the worst case complexity for the last one is to be linear?
Not the worst case, best case.
Oh, best case. Okay. So what will be the worst case will be n square?
No, nk, because every step you are eliminating the k, right?
Okay.
You're eliminating one value. Like if I ask you to find the fifth largest number, right? And you end up like having terrible luck that you always find the largest number in your thing, it will always end up in case 3, right?
Okay.
And then in case 3, you will essentially keep going over and over again, and finally you will reach that. So that will essentially be case. Nk is the worst case. Okay, and the best case would essentially be O of n, which is like for each loop. And let's assume that you somehow the best case is like you find it in the very first turn itself, right? As your luck would have it, you found the exact pivot that breaks it into 2 parts. Okay. Yeah. Or you found it in 2 iterations, or you found it in 3 iterations. So it's essentially in some finite iterations before k, you will find it. So in a typical case, it is O of n. Okay, unlike the heap where it is actually O of n log k.
Right. Yeah. Okay. Yeah. Thanks.
Make sense?
Yeah.
Vivek, one quick question, Vivek.
Go ahead, Shrikant.
Yeah, for this, by using the QuickSelect algorithm, so for solving the problems 1, 2, and 3, we can use it the QuickSelect also, right? In any case.
Yeah. This is just a general case, right? You are solving the QuickSelect actually solves 3.
Yeah. Okay.
And put k equal to 2, you got 2, and put k equal to 1, you got the first one, right? The only thing is that you have a O of n definite solution for the first and second.
Okay.
So you may actually be making it a little worse in some cases.
Yeah, but for those 3, we can't able to use the QuickSort algorithm, right? For the k position, we can't able to send it for the QuickSort, but QuickSelect is the best feasible algorithm for those whatever the second and third problems. QuickSort
is actually not meant for the first 1, 2, and 3. I just want
Yeah, only the sort for sorting only.
That just does the sorting. So you can sort and find it, but the sorting complexity is best case is n log n in that case, right? So it doesn't really give you any advantage. The only reason why I wanted to do the QuickSort algorithm walkthrough in this session was so that we actually have a foundation of what QuickSort does, and then use it to build the QuickSelect algorithm.
Okay, got it. Thanks, Vivek. Thanks a lot.
Awesome. Any more questions? All right, fantastic. So what I'm going to do is I'm going to turn off the recording. Now, if folks have any questions, feel free to ask. I'm here to answer.